define physical intelligence. I would just imagine that organisms we see in nature have some kind of physical intelligence. And so we're trying to understand what kind of system will evolve and behave like an organism. From the physics point of view, if you look at what we've done in the last few centuries, with physical intelligence and biology in the background, we can see physics is broadly classified into Newtonian mechanics and in 20th century quantum mechanics. And on the other end, there is thermodynamics. And I want to contrast these two. Mechanics, or Newtonian mechanics, is based on reversible laws. In other words, if you take a movie of a physical process and run it backwards, no physical law is violated. Both processes are possible. They may be improbable, one may be improbable, but not impossible. And that is our dominant view. And that view has led us to create a world of machines and computers, in which the irreversible processes, which are like friction, heat generation in your computers, all those things are undesirable. They're bad things. If you eliminate friction and all that, you have perfect clock that will go on forever. And that is the world you have created. And we can see it all around us. And it is nothing like the natural world. Though we now want to portray the natural world as a kind of machine, which I think is a wrong approach. The world of thermodynamics, on the other hand, is based on irreversible laws. One of its most fundamental laws is the irreversible increase of entropy. And thermodynamics is based on two concepts, energy and entropy. This subject originated in the 19th century to understand the workings of steam engine, the conversion of heat to motion. But in the 20th century, it gave us another remarkable insight, that these irreversible processes that generate entropy, in fact, can create order spontaneously. These are called self-organization in physical and chemical systems. And these systems continuously generate entropy. The most undesirable thing in machines becomes the most fundamental thing in self-organization. I'll show you an example. And these irreversible processes can generate a structure spontaneously that resembles physical or biological organisms. And therefore they are called dissipative structures because they are constantly generating entropy and dissipating energy. Let's take an example of a simple clock. Most of you have probably taken a course in physics in which the great accomplishment of mechanics is the simple pendulum, like the clock. Newton's mechanics describes this beautifully. If you ignore the friction, it will go on forever. But in the real world, it will never do. On the other hand, there are clocks in nature, biological clocks. There are no pendulums, there are no balance wheels or quartz crystals. The clocks in nature are chemical. The beating of a heart, the flashing of a butterfly, the firefly, the wind motion, all those things are driven by chemistry. So you all have seen clocks, but I'm going to show you the next slide, the chemical clock. All you do is put a bunch of chemicals in the beaker because the magnets are constantly stirring. There's no design, no balance wheels, nothing. And it's oscillating between red and blue. It's a clock. That's more closer to the clocks we see in flashing butterflies, circadian rhythms, and all those things. And nobody designed this clock with any mechanical means. And what is important in this clock is that it is run by dissipative processes, and it will work only if it's continuously generating entropy. And there are some comments about it. I won't go into detail. So here is a chemical flow. So with this example, I want to contrast the world of mechanics and the world of thermodynamics. So the first point I already made is generally based. The world of mechanics generated machines and computers. So I'm going to call them design structures of machines. The world of thermodynamics can give us dissipative structures. I want to contrast these two. The world of mechanics is based on reversible laws and computer logic, where the logic is actually outside the system. It doesn't have, the system by itself doesn't have a system, a logic that it builds. We build the logic into the system. It has no intelligence of its own. Its intelligence really lies in the program. Distributed structures is based on irreversible laws. The structure of machines is an external process. Somebody else designed it. Distributed structure, we don't design anything. The system itself designs, and we need to have no control. We can only look at it and marvel it, and if you understand its behavior, maybe use it. But we can't control the design that much. We can perturb it a little bit, but in most of the cases, we can't really predict what it's going to do. For design structures, entropy generation is undesirable. For dissipated structures, it's essential. If you turn off entropy production, the whole system dies. It's similar if you starve an organism, it dies. And when it consumes food, it's burning energy and it's dissipating energy. And most important, you say, well, my car also dissipates energy. What's the difference? In your car, the energy dissipated is not used to maintain the car, to build the car. In an organism, the energy is used to build itself. Usage of energy and the construction, they're all integrated. The last but one feature, which is quite important, is in machines and design structures. It has one specified function, and if you change the environment and disturb it, it won't be able to accomplish that function. If one part doesn't work, the machine stops. This feature we'd like to call, I don't know the origin, I heard it in my theory, is function-specific variability. It is specific to the function, but it will accomplish the same function with many different means. I'll show you in a few minutes an example of how this comes about. In organisms, this is not the case. They will accomplish the same function in many, many different ways. In a machine, it can accomplish that function in one and only one way, generally. If you change something, you write one wrong code in a computer program and the whole thing crashes. And that limitation actually keeps millions of people in business. And in biological organism, one little thing might fail, but it continues to live somehow. People can, organisms can live without a limb. If their heart is weak, the other part of the heart takes over, and it continues to live. There is no such analogy in living things. So the same function can be accomplished in many, many different ways in the living system. So what I'm proposing is organism, like behavior, is a subset of dissipative structures. So what is needed? We know thermodynamics. What's needed? The structure must contain a large number of internal states. And in addition to some kind of external thermodynamic force that drives the system to organize, it should be able to build its own internal states. And these two concepts give rise to what I call functional symmetry. So the best thing is to give you an example of it instead of describing it more. The concept I'm describing will be described in more detail in James Dixon's talk. He'll show you a system that illustrates all these points. But I'll only give you an introduction to it. The concept of functional symmetry breaking and thermodynamic forces. You will see in the example that there's an external voltage that drives the system, the 30,000 volt system. There's the external force, just as we need sunlight to run our whole system. But in addition to the external force, internally, there are other little forces that come about. And if these forces are sufficiently large in number, the system will self-organize and create its own internal structure. When it does that, each one of these subsystems have a slightly different function. They are no longer similar. In the upper picture, each one is not very different from the other. In the lower picture, they're organized, and each one is located in a slightly different place. So let me show you, to conclude, this example of how this happens. Here is a system that's driven by external voltage. And the upper arrow is an electrode, it's spraying charges. And the lower, these just ball bearings in cooking oil. There's a ring electrode, and the current is flowing from the center upper electrode to the ring electrode. That's it. And the ball bearings organize themselves, and their goal is to collect charges as their food. And as you can see, they're moving around and collecting food. And because they organize themselves, each one of those beads has a slightly different function. The beads at the tip are collecting charges, the other beads are transferring charges, and their goal is to move the charge to the electrode on the periphery. And each time they have the same goal. They will maximize the current. They find a structure that will maximize the current. And if they deplete the charges here, it goes to the neighboring charge and picks up the charges. Now we can all describe this using physics. Oh, there's a field here, this field has changed. When the charges are depleted, the field strength decreases, so it's moving it, just like we can describe living things with chemistry. But as Albert Rosen pointed out, analysis is not equal to synthesis of living things. You can understand how it works, but you don't know how to build it. If you take a camera apart, you understand how it works, you also know how to build it. So, in this case, we don't have control of it, but you can see organism-like behavior. So, to conclude my talk, my main point is thermodynamics and the concept of dissipative structures, and what that part of physics is what is needed to build a theory of physical materials. Thank you.
Time for the end. Let's move on to our second speaker.